Today we are going to study about thiophene. Thiophene is a five-membered heterocyclic compound which have sulfur as a heteroatom. Eh, The properties suggest that thiophene is aromatic. Let's check how it is. Thiophene have four carbon atoms which are sp2 hybridized, and each of those carbon atom have a unhybridized p orbital containing one electron, while the sulfur atom that is also sp2 hybridized orbital, it has one unhybridized p orbital having a lone pair of electron and a sp2 hybridized orbital containing a lone pair. Now, the unhybridized p orbitals are perpendicular to the plane of the ring. Now, why I am saying plane of the ring? Because all the atoms involved in forming this ring are sp2 hybridized, and sp2 hybridized is a planar structure. So this ring is planar and these p orbitals are perpendicular to the plane of the ring. Now, second condition is there should be overlapping of p orbital. Since these p orbital are parallel to each other, so there is a possibility of overlap of electrons. Now, for aromaticity, we have three conditions. That is, the compound should be planar. It should have a delocalization of pi electrons, and it should have 4n plus 2 pi electron. That is Huckel's rule. Now, let's see, in the thiophene, we have 4 carbon and 1 sulfur. All of those are sp2 hybridized. So they are planar. And we can say the thiophene ring structure is planar. Each atom have a p orbital which is unhybridized and it is perpendicular to the plane of sigma bond and parallel to each other. So the overlapping is possible between the p orbital. Third thing, there are total 6 pi electrons, 4 from the carbon atoms and 2 from the sulfur. So it is fulfilling the condition of 4n plus 2 pi electrons. So we can clearly state that thiophene is an aromatic compound. Now, if we have to compare the aromaticity of furan, thiophene, pyrrole and benzene, how will we arrange them in an order? From the screen, you can clearly see that benzene is the most aromatic here and furan is the least aromatic. First of all, discuss the case of benzene. In case of benzene, all the atoms are same, that is carbon. So the distribution of pi electron is uniform. While in the case of furan, pyrrole and thiophene, we have a one heteroatom other than the carbon atoms. So the distribution will not be uniform. Now, if the heteroatom is more aromatic than the carbon, then it will hold the pi electrons more tightly and will lower the ease of delocalization. Also, we can say that the heteroatom which is more electronegative out of these three, that is nitrogen, sulfur and oxygen, that atom will bind the electrons more tightly, hence in turn decreasing the delocalization. So the oxygen is the most electronegative, then nitrogen, then sulfur. So the ease of delocalization will decrease from sulfur containing to nitrogen containing and then furan, that is oxygen containing heterocyclic atom. So what is happening here? Here we have benzene that do not have any restraint in the delocalization of pi electron. So it is most electronegative. Then comes the sulfur. Since out of nitrogen, oxygen and sulfur, sulfur is least electronegative. So it will restrain to a smaller extent. It will restrain the delocalization of pi electron to a lower level, smaller level than nitrogen and then oxygen. So our second most aromatic compound is thiophene, then pyrrole, then furan. So from this we can clearly state that the order of electronegativity affects the level of aromaticity. Higher the electronegativity of heteroatom, lower will be the aromaticity. So in this case, our furan is least aromatic. Now comes the synthesis of thiophene. This Paal-Knorr synthesis we have seen in case of pyrrole, in case of furan, and now in case of thiophene also. So what is happening? Our reactant 1,4-dicarbonyl compound is same in each of the cases, but the other reactant or conditions are changing. Here in the case of thiophene, we are reacting 1,4-dicarbonyl compound with P2S5 at an elevated temperature. And the role of P2S5 is to provide sulfur. It's a source of sulfur. So let's see the mechanism here. What is happening when we react our 1,4-dicarbonyl compound with P2S5? It replaces one of the carbonyl oxygen with sulfur, resulting in the formation of thioketone. This thioketone further cyclize by using the lone pair present on the sulfur. What is happening here? This structure is taking a proton from the solution. Since your oxygen is more electronegative as compared to sulfur, so proton will attach to this oxygen atom and form OH positive. Now what is happening? Your sulfur have a lone pair of electron and this structure is not stable. So this lone pair of electron will attack the carbonyl carbon and your OH will form. This double bond, the pi bond will cleave and it will form OH and sulfur will form a bond here. And in order to facilitate that bond formation, this proton will be lost here and these bond pair electron will come here and this double bond will become single bond. So this is the structure we are getting here. Now on losing one water molecule, we are obtaining a aromatic structure and this is the substituted thiophene structure. The detailed loss of water molecule has been discussed in the two previous classes in case of furan as well as in case of pyrrole. So I'm not going to explain each and every step involving here. Please go back to those videos if you have any doubt. Now second synthesis is from sodium succinate. This is the structure of sodium succinate. It's a laboratory process and in the laboratory what they do, they mix sodium succinate with phosphorus trisulfide, that is P2S3 at an elevated temperature and obtained your thiophene. This is very useful if you want to prepare a unsubstituted thiophene. Third is Hinsberg synthesis. In the Hinsberg synthesis, condensation reaction occur between 1,2-dicarbonyl compound and diethyl thiodiacetate. Now from the structure you can clearly see this is 1,2-dicarbonyl compound and this is your thiodiacetate. In a presence of base, the condensation reaction occur and what happens? Your from the color scheme, you can clearly see that these two oxygen atoms are involved in condensation, and here we have two carbon atoms. Sorry, here we have two hydrogen atom attached to these carbon present next to the sulfur atom. So the two hydrogen from here and one oxygen atom of the dicarbonyl compound are lost, and the remaining carbon atom are involved in forming this ring structure here. From the color scheme, you can identify which part is where. So what is happening here? The thiodiacetate loses two hydrogen atoms from here, and they take oxygen atom from the dicarbonyl compound and loses it as a water, and the remaining structure combines to form a thiophene diketones. So Heisenberg synthesis is basically used in the synthesis of thiophene diketones. If we change the structure here, this was the journal reaction here. If we take benzyl and diethyl thioacetate, what we will get? We'll get this kind of structure, and what is happening here? The oxygen and water molecule are losing, sorry, or the oxygen and hydrogen atoms forming water molecule, and the remaining entities are involved in synthesis of your substituted thiophene. Now reactions. So the reactions are similar to the furan and pyrrole. Your thiophene also forms a C2 substituted products during electrophilic substitution. Let's see, if we have a very strong acidic condition, then the polymerization occurs. This is the example of action of hot sulfuric acid on thiophene, and it results in the formation of trimer. Here are the nitration, sulfonation, chlorination, and reaction of acetic anhydride. So what is happening here? In case of pyrrole, you had seen that one only one product was forming here. But in case of thiophene, but in case of thiophene, we get two nitration product, one sulfonation product, and two chlorination products. So these, in the case of nitration, your C2 substituted product is major product, while the other one is minor. Same is the case with the chlorination. Now, if we do reduction reaction, so here in the case of thiophene, if you're using nickel as a catalyst with hydrogen gas, the cleavage of ring occurs and butane formation occur while the sulfur bonds with the nickel. And if you use platinum as an as a catalyst, you will have tetrahydrothiophene as a product. Now, if we react it with the organolithium compound, two thiophenyl lithium will form, and on further reacting with the carbon dioxide in presence of acid, thiophene 2 carboxylic acid formation take place. This is the similar kind of reactions are given by alkenes also, where organometallic compounds are reacted with the alkenes, and then for the different reagents gives different substituted products. Now some medicinal uses of thiophene. Now, if we see the structures here, these are the drug molecules. This is for the cetexen- cetexentan. And here, your thiophene molecule is present here. Now, if you can see in the structure, there are more than one heterocyclic compounds. One is your thiophene, other one is your this, where you have one oxygen atom and one nitrogen atom, and it's a five-member ring, and it has unsaturation. So, in nomenclature, we have discussed the name of this compound. So, what this drug do? This is used as a cardiovascular agent, and it is used in pulmonary artery hypertension. So it's for the high blood pressure condition. This drug is used. Another one is tiagabine. Tiagabine is an anti-convulsant agent, and it is used in the treatment of epilepsy. Epilepsy is मिर्गी के दौरे आते हैं, सुना होगा, you would have listened that. So it is used in the treatment of epilepsy, and here also we have two different kind of heterocyclic compounds. One is one is the thiophene, which is present twice. Another one is this, and this is the derivative of pyridine. So what is happening here? Third kind is articaine. This is anesthetic agent, and clearly from the structure you can see this is thiophene present here. All right.